In this video, we're going to be looking at magnetic force and how to determine the direction of that force using something called the right-hand rule. Now, we know that anytime we have a charge moving through a magnetic field, it's going to experience a force. Now, how do we know this? Well, remember that moving charges create magnetic fields. And when one magnetic field interacts with another magnetic field, they're going to move. They're either going to attract or repel, but there is going to be a change in motion, which is due to a force. Now, we can use the right-hand rule to find the direction of this magnetic force. Now, I'm actually going to give you 3 right-hand rules to use in different situations. Keep in mind that my rules might be slightly different from another person's. If you go and look up tutorials online, theirs might be a little bit different. They might not number them. They might not have the same numbers as me. Their hands, the shapes of the hands might be a little bit different. There's variations, but these are my right-hand rules. Also, use your right hand for these, not your left hand. There are situations where you use the left hand when you're dealing with negative charges, but we're not going to be doing those in this section. So you are only going to be using your right hand for these. Now, for the first right-hand rule that I'm going to show you, this is anytime you have a coil of wire. So if you have a coil of wire like this attached to a battery, you can figure out from the direction of current which way your magnetic field is going to go. Now, first of all, your hand is going to be in the thumbs up shape. Your thumb will point towards the north pole of the magnet, and your fingers curl in the direction of your magnetic field. So let me draw you an example. I'm going to start with a little rectangle here. And let's see, how do I want to do this? I'm going to do this example by giving you the current. Okay. Now, the way I've got this wrapped, the way I've drawn this is that the coil, the wire, wraps up in front and then down back behind, like that. Now, if I tell you that the current is going in on this side and out on this side, we can use this rule to figure out which side of our coil is the north pole. So again, hand is in the thumbs up shape, thumb is your north pole, fingers curl in the direction of your current. And I usually that little rectangle there, I usually pretend that my pen is that little rectangle. So my current is going up in front and then down back behind it. So if this side is the front, my fingers are going up in front and then down behind. And when I grab my pen like this, it makes my thumb point to the left side. Therefore, this would be the north pole of my magnet and this would be the south pole of my magnet. You can also go the other way. So let's say you know that, let me draw another example here, and I'm going to go this way. Let's say that you know this side is the north pole and this side is my south pole. Right-hand rule says my thumb needs to point to the left because that's where my north pole is. And my fingers go up in front, down behind. So with this one, if it needs to go up in front and down behind, this side is going behind it, so it's going down on this side, up on this side. Now let's look at a few more examples of this. I've already prepared some drawings. So let's just follow along and see if you can get the same answers that I do. With this one, I gave you the north and south poles. Now again, right-hand rule, says that your thumb points towards your North Pole. So again, my fingers go up in front, down behind. So up in front means my current is going in on this side because this wire is going in front, and then down behind. Okay, let's look at that one. Again, my North Pole is on the left side, so again, up in front, down behind. This one has the current going in on this side and out on that one, because again, this wire is in front, and with your thumb pointing left, it goes up in front, down behind. Now, if you know the direction of the current, and I just noticed that I did not put a current on my last drawing. Okay, there we go. Now, going to this one. Here, I know my current. My current is going up behind my coil and then down in front. So if I make my fingers do the same thing, my fingers go up behind it, down in front. This makes my thumb point to the right side, making this side the North Pole and this side the South Pole. Similar idea here. Up in front, or up behind, down in front, makes my thumb point to this side. Okay. Now the second rule I'm going to show you is anytime we have current going through a straight wire. Now your hand again is in the thumbs up shape, but this time your thumb points in the direction of the current. Now I usually, when I do my drawings, I usually indicate current with the letter I, because in the formula current is represented by the letter I, and I do B for magnetic field. In our previous section of notes, I said that magnetic field is represented by the letter B in a formula. So we're going to do that. So let's say I had a wire with current going through it, and the current in the wire is going up. I can use this rule to figure out the direction of the current. So for instance, with this example here, my thumb points in the direction of my current, which is up the paper, and my fingers show the direction of the magnetic field. Now, in this particular example, my fingers, if I grip my pen using this to represent the wire, they're going left behind the wire and right in front of it. So it's going something like that. Left behind the wire, right in front of it. Now, let's say I had an example of current that was going into the paper. Now, we talked about the dots and X's in one of the previous sections. A dot means whatever it is, whether it's force, magnetic field, or current, is coming out of the page. And the X means it's going into the page. So with this example, I have current going into the page. So when I have my thumbs up shape, my thumb for current is going to go into the paper. This makes my fingers wrap around this direction, clockwise. So my my magnetic field is going clockwise around the wire. Now again, I've prepared some other examples, so let's do a few more. If you want to see if you can get the same answer as I do as we work, follow along. So in this one, I gave you current on these two. With this one, my current is going to the right, so when I do this, my thumb will be pointing to the right for current. My fingers, if I use my pen as the wire, are going up behind the wire and down in front of it. So again, up behind the wire, down in front of it. It's going like that. This one, the dot means it's coming out of the page, so my thumb is going to come this way, pointing out of the page, and my fingers are curling counterclockwise. So that's the direction of my magnetic field. Okay. And you can go the other way. So you can probably already tell that these are the magnetic field I drew here is similar to this magnetic field. So what I've given you is the magnetic field, the fingers. What you're going to figure out is what direction your thumb points. So with this one, my fingers are going to be curling clockwise. And to have that happen, my thumb has to be pointing into the paper. So the current is into the paper. You can either do the symbol or you can just write into the page. Either way is good with me. So this one I gave you the magnetic field, and you have to determine the direction of the current in the wire. So this one, you can see that it's kind of going to the left as it goes behind it. So to the left behind the wire makes my thumb point up. So my current is going up. Now one more thing. When you're doing problems like this and you're trying to label what describe what direction it's going, top of your paper is up, bottom of your paper is down. Okay? So if something's coming out of the paper at you, that's not up. Up is towards the top of your paper. Alright. One more right-hand rule. Anytime you have magnetic force involved, you're going to be using right-hand rule number 3. Now this is the only one with a different hand shape. With this one, your hand is flat, like you're saying stop. Your thumb is going to point in the direction of your charge. Most of the time I will label it with an I. It's not necessarily current. It could just be a single charge, but I tend to label it with an I. The fingers point in the direction of your magnetic field, which again is B. Your palm is going to be your force, F. So let's say I had a problem where I had a magnetic field going up the paper and a charge going to the right. And I wanted to know what direction the force was going in. Well, with this one, you have to align both your, you have to align 2 out of the 3. In this case, my fingers for magnetic field and my thumb for current. So my fingers need to point up the page. And then keeping them pointing up, I need to rotate it, rotate my hand so that my thumb points to the right. And that was really dumb of me. Fingers up, thumb to the right. Sorry. Makes my palm face towards me. That is out of the page. If you like, you can use the dot to represent that, or you can describe it in words. Let me show you another example. Let's say I had my force going out of the page and my magnetic field going down the page. If my force is coming out of the page, my palm needs to face towards me. Now, keeping my palm facing up, I need to rotate my hand so that my fingers for the magnetic field point downward. So, keeping my palm up, rotate so my hand points, my fingers point downward. This makes my thumb point to the left side of the paper. So my current is going left. Okay. Let's do some more examples that I have prepared. So starting with this one. With this one, my force, the X means it's going into the page, so my palm for the force needs to go into the paper. At the same time, my fingers for the magnetic field need to go to the right. So keeping my palm down, I'm going to rotate my hand till my fingers go to the right, which makes my thumb point up the page. So my current is going up. With this one, I have the current, which is my thumb, and my magnetic field, which is my finger. With this one, I need to make sure my fingers are pointing left, but my thumb points up the page. So keeping my fingers pointing this way, I can rotate my hand here to make my thumb point up my paper. This makes my palm face me. So my force is out. Is coming out of the page. Right? In this example, I have current and force. My current, which is my thumb, is coming out of the paper, like that, and my force is going down the page. So keeping my thumb pointing up out of the page, I have to rotate my hand so my palm faces downward. This makes my fingers point to the left. So in this example, your magnetic field is going to the left. Okay, now this one, if you look, we have force and magnetic field. Force is your palm, magnetic field is your fingers. So my fingers need to face to the right with my palm facing up. My thumb, which is the current, is pointing out of the page. So your current is out of the page. I think I'm going to change this one. I'm going to change this to an X. Okay. Now, with this one, my current, my current is going to the right, so my thumb needs to point right, and my fingers for the magnetic field are going into the page. So my fingers are going into the page. And with my fingers going into the page, I rotate my hand to make my thumb for current go to the right. This makes my palm face up the page. So my force is going up the page. In this last example here, I have force and current. So my palm and my thumb. I need to figure out which way my fingers go. So my palm for force is coming out of the page. So I need to have my palm facing towards me. My thumb is going to the right for the current. This makes my fingers for the magnetic field point up the page. So magnetic field is going up. Now, one more thing I didn't put on here, but I'm going to do another quick example. You might sometimes see, instead of writing or drawing an arrow or a symbol to represent the magnetic field, sometimes it'll just tell you that a charge is moving between two magnets and we want to know what the force is. Well, you have to remember that magnetic field lines always point away from a north pole and towards a south pole. Okay, so if you see a problem like that, you got to remember magnetic fields always point towards the south pole. So with this example I just drew, my thumb is coming out of the page with my fingers for the magnetic field pointing to the right, which means my force is going up. Alright, so I've done several examples for all of my rules. I'll give you some practice for that later. But let's finish these last two slides of Chapter 19, Section 3. Now, with this one, anytime you have two parallel wires that are conducting current, they will exert a force on one another. Now, they're either going to attract or repel. So let's say we had two wires with current going in the same direction for both of those wires. Now, if we use right-hand rule number 2, we can determine the direction of the magnetic field around these wires. Now, with this rule, your thumb is your current, your fingers are your magnetic field, and your hand is in a thumbs-up shape. So, with my thumb as the current going up the page, my fingers are the magnetic field going around it. So it's going left behind, right in front. Kind of like that. This one is also going in the same direction. But if you look here, my magnetic fields in between them are going in opposite directions, and since opposites repel, these two wires will attract. So if you have current going in the same direction in two parallel conducting wires, they will attract one another. Now, if we have current in the two parallel wires going in opposite directions, they're going to repel one another. I'll show you why. Now, this one, I have a drawing going up like the others, so I'm just going to copy down what I already had there. Now, for the one going down, right-hand rule, thumb going down, fingers go left in front, right behind, makes it look like the magnetic field goes that way. And if you look between them, my magnetic fields are going in the same direction. Likes repel, so these two wires repel. Now, magnetic force has a lot of different uses. One of the simplest examples, of course, is a compass. Okay, it's the magnetic field lines from the Earth. Move the magnet of the compass, points north. That's an easy one. If maybe you have a grandparent or somebody who just has a really old TV, well, I wouldn't recommend doing this. It can mess up the television. But old style TVs used to have, they had cathode ray tubes, which basically takes a stream of electrons and uses it to make a picture on the television. But if you ever took a magnet and got too close to one of those, it would actually mess up the picture, because the magnetic field from the magnet interferes with the stream of electrons and distorts it and messes up the picture. Let's see. Loudspeakers. We use magnets in loudspeakers. When the current through loudspeakers have a coil of wire going through them, and there's usually another magnet in there. And when you have current going through the coil, it creates a magnetic field inside the coil, which is either going to be attracted or repelled to the other magnet inside the loudspeaker. And by changing the direction of the current, you're changing the direction of your magnetic field, so the coil ends up moving back and forth, which moves the cone and produces vibrations, which is what sound is. Sound is just vibrations. Okay, there's also something called a galvanometer. I think my pen is running out. Let me change it out. There we go. A galvanometer is something used to create ammeters and voltmeters, which are used to measure current and voltage in a circuit. And it's a similar concept. Usually there's a coil of wire in a magnetic field, and when you have current entering the coil, it produces its own magnetic field, which interacts with the magnetic field around it and causes the coil to twist. The stronger the current, the stronger the magnetic field in the coil, and the more the coil will twist. So it allows us to read how much current and therefore how much voltage is in the circuit. Alright, so that's it for section 19.3.